Good afternoon, everybody. I am Dr. Vinita Gupta. We extend a very warm welcome to all the participants of this online course on Advanced Materials Chemistry. This course was floated last year for the first time and garnered an enormous response. And this is basically due to wide coverage of the topics that it addresses, which makes it useful to researchers from wide-ranging scientific fields. And excellent feedback was received on the course, and that has prompted HPNI to float it for the second time this year. So basically, this year we do not have any formal inauguration, but it was thought that it would be good to have a small introductory session with the participants. So to kickstart the course, we have with us none other than Professor A.K. Tyagi, Director Chemistry Group, Bhabha Atomic Research Center, who is also the director of this course, as all of you know. Professor Tyagi is himself a very accomplished and decorated material scientist who has received several national and international recognitions for his immense contributions to solid-state chemistry. I would now request Professor A.K. Tyagi to address the participants and give a brief overview of the course. Sir, please.
Cursor. Thanks, Vinita. And let me also welcome all the participants who have joined online, and a very good afternoon to you all. So as she already pointed out, that in short presentation of about half an hour, I am going to give a broad overview of what is in the offing in this course. And this I will do by posing a question, namely, what is materials chemistry? And while answering this question, I'll give you overview of this course. Evolution of humankind is extremely intertwined with materials. You can see from this slide, various ages through which humankind have gone through are named according to the material used by them. To begin with, we had Stone Age, Bronze Age, and Stone Age had an engineering method, physical processing. Bronze Age followed by Iron Age. We had forging. Those people knew how to forge bronze and iron. Then came Steel Age. The process was smelting, turning. Silicon Age came into existence about 5 or 6 decades ago. This is also called as Information Age. People knew how to do micro and nano fabrication. And these days we talk about atomistic manipulation of materials, wherein we know how to tune material at the level of atomic dimensions. And this is done by laser manipulation. Stone Age persisted for several millions of years. Subsequent ages did not last for beyond a few tens of millennia. And as of now, no age is going to last for more than perhaps 30 to 35 years, because so much of progress in this field is there that you will always have a new material which will lead to new age. History of material. It was discovery of Iceman in the Alps in 1991, which gave significant information on early copper age, because this body was having a copper X, as you can see in this photograph. So the first metal tool appeared perhaps only about 6,000 years ago. Before that, people had, as I mentioned, stone as the main material used by them. Materials that change life forever are shown in this slide. We have wood, clay, fiber, bronze, iron and steel, glasses, paper, plastic, aluminum, semiconductors. These are the materials which, according to me, have changed our life forever. So let me begin with iron. Why iron is so special to humankind? Definitely not because it is hard or it is strong. On the contrary, iron is a reasonably soft and malleable ductile element. It is because iron has got a universal property by which one can play with and properties of iron by fine tuning heating and cooling rates. So heat treatment can impart a wide range of properties to iron, and also by microalloying you put a small amount of some other element, be it metal or non-metal, can lead to drastic change in mechanical strength of iron. It is this unique ability of iron which was used by our forefathers to make all types of devices, you can see weapons, etc., using iron as the base material. From iron to steel, there is a very exciting journey. Crystal structure of pure iron offers a very little resistance to the iron atoms slipping past one another, and that's why it is quite ductile and soft. The array of atoms in iron can be moved by exerting slight pressure, slight force. Steel is a metal alloy that is principally composed of iron and carbon. So a very small fraction of carbon is introduced, a few atom percent of carbon is introduced in the lattice of iron, and this carbon goes and it occupies the interstitial voids, and this prevents the moment of dislocation, and hence you have got much more strength you impart to iron which was otherwise soft, ductile and malleable. So this is the advantage of knowing the concept of substitution. All this is going to be taught to you in this course. How to select a proper dopant and how to select the extent of doping. These are the things which our faculty members will teach you. Steel has been only during last 150 years in existence, but its growth is unprecedented. No other material can come close to steel in terms of amount of production. Let me change the example from steel to evolution of memory devices. We ourselves have seen how this evolution has taken place. Magnetic tapes, delay line memory, hard disk, audio tape, floppy disk. My generation has used them. My generation has used this onwards. Compact disk, mini disk, DVD, SD card. Now we talk about cloud backup. All this could be realized because of advancement in the field of materials chemistry. So this you see the miniaturization of memory devices which led to digital revolution. 1950s silicon transistor had only one chip. 1960s it became 16 transistors, and then you see the exponential growth. And now we have got billions of transistors, and here comes the saturation of what is called as Moore's law. Now, to go beyond Moore's law, one has to go for quantum computing. And in BRC, work is going on in this direction also. Second major revolution which happened in mankind was rechargeable battery miniaturization. Lead acid based batteries, 1859 they were discovered, and they are in use even now also. Nickel cadmium batteries were developed in 1899. Mobile batteries are there in pockets of all of us. Paper battery, which can be flexible, you can fold it the way you want. Coin cells, followed by very small implantable batteries. These batteries can be implanted in our body for various biological requirements. All this also has happened because of advancement of materials, and there are going to be lectures on development of battery materials. Major discoveries in the field of materials during last about 3 decades, which I have myself witnessed. Lithium-ion batteries were discovered in 1980s. Nobel Prize came a bit late, 2018. Molecular machines, blue light emitting diodes, graphene, CMR materials, conducting polymers, full range, and high TC oxides. So all these discoveries fetched Nobel Prize. And here I may add synthesis and characterization techniques played a key role in discovery of these Nobel Prize winning materials. In our course of 30 lectures and 6 credits, you will have dedicated portions dealing about synthesis and all types of different characterization techniques. This is one of the highlight of our course, wherein people who have spent 2 to 3 decades are going to teach you synthesis protocols and how to characterize these materials. Contemporary material science, we talk about this these days. It consists of functional materials. There is a dedicated course for this. High-end materials, hybrid materials, energy material also. There is one package on this in our course. Engineered materials and materials for society. All these 6 major segments of contemporary material science are going to be discussed as the course unfolds. Materials for sustainable life. These days, there is a lot of emphasis on developing materials for sustainable life. In this case, our faculty members are going to teach you materials for health sector, namely disease diagnosis, nano drug carriers, new small drug molecules, etc. Energy sector, about materials for energy harvesting, storage, transportation, and biofuels. In the field of environment, there will be lectures on protocols for reduction in carbon credit, nanopesticides, conversion of polymer to monomers. Earlier, we were keen to develop a catalyst for efficient conversion of monomer to polymer. But having got so many polymers, millions of tons of polymers are there as of now. So how to get rid of them? The best course of action is there. Once their life ends, can we develop protocols to get back respective monomer from them? And if that happens, that is going to change the life forever. Role of chemistry in energy challenge. I'll give a very brief overview. More details you will learn from the concerned faculty members. In energy conservation, we have to work on sustainable production of energy, process for recovery of valuables, materials for electronics and lighting. Fossil fuels, we have to develop protocols for better coal combustion, CO2 sequestration, followed by its use. There is a concept wherein carbon dioxide can be converted to hydrocarbons. These kind of things will be touched upon in this course. Petrochemistry, chemical feedstocks, nuclear materials, for example, materials under extreme conditions, materials which can withstand high radiation field are the concepts which will be introduced to you, followed by nuclear waste management. In case of renewable energies, there will be an emphasis on chemical storage, hydrogen storage, battery materials, already I have mentioned, fuel cells, syn fuel, biomass, chemical feedstock has come here also, and solar energy harvesting. All these things will be exposed to you in coming days. Role of chemistry, in particular materials chemistry in healthcare, is going to be very important. Here, work is going on in our department for development of radioprotectors, nutraceuticals such as curcumin and its analogues, natural product extracts, organoselenium compounds, enhancing the bioavailability of, for example, curcumin. Curcumin is the active molecule in haldi, which has been known to us for ages. So how this curcumin bioavailability can be increased, all these things will be taught to you. Synthetic chemistry for new therapeutics such as platinum and selenium based drugs, deuterated drugs, magnetic hyperthermia, photothermal therapy, etc. are also going to be covered. Some novel drug delivery systems such as nanogold, Fe3O4, silica, all of them are biocompatible. Ribosomes, micelles, and hydrogel-based nano drug carriers will be taught to you. As far as diagnosis of cancer is concerned, there are devices like extracellular acidity measurement device, quadruplex sensors, surface plasma resonance based sensors, and luminescent materials. Some of these things, if not all, will be covered in this course. Role of chemistry in environment. In fact, all three of them call for dedicated courses. The main aim of this course is to provide you a broad overview. Subsequently, we will definitely conduct dedicated courses for energy health and environment sector also. Air and soil, CO2 sequestration, persistent organic pollutants, POPs, how to sense them, how to degrade them. These are the protocols you will be taught. Water remediation, what are the techniques available at your disposal, agro-based sorbents, etc. are also going to be taught, some of them at least, if not all. So, as I mentioned, that one of the major portion of this course is going to be on functional materials. Many young students might be wondering what this term is all about. So let me spend a minute or two to explain to you what are functional materials. In this slide, you have seen I am arranging 5 different types of material. For example, tin oxide is semiconductor. It is used to develop sensors for toxic gases like ammonia and H2S in air. In this case, resistivity of tin oxide is measured, which translates into the concentration of ammonia or H2S in air. Next is yttriadothoria YDT, an insulator. In this case, we measure ionic conductivity, which gives us the value of sodium in water. It is used in fast breeder reactors. Calixarine is an organic compound. In this case, an electrochemical signal is measured, which translates into the concentration of cesium-137 in nuclear waste. Silver rhodamine 6G is a hybrid material, optical sensor basically, and this gives us the quantitative presence of lead-2 plus in potable water. Conducting polymer is a novel discovery, you all know, organic compound. Here, conductivity of conducting polymers as a presence of progesterone is measured, and in turn, you find out the presence or absence of progesterone antibodies in our body. So, in previous slide, you have seen that 5 different materials were classified in same table. They have nothing in common. Their structure, bonding, origin, properties, everything is different. Still, they were clubbed together because they have one common function, and that is they all are used in sensing. So they are sensor materials. So this is the new classification of material wherein we club materials based on the function which they can do for you. And that's how we define functional materials. In our group, we basically design functional materials based on rational approach. This can be a crystallographic approach, a metastable approach, defects engineering, and hybrid approach. So these 4 approaches will be taught to you in this course. And in today's short presentation, I will show one slide each of these 4 approaches. First one, let us see how crystal structure and chemical bonding are mother to all the properties can be seen from this slide. This slide you see the structure of alpha alumina, corundum structure. So it is hexagonal. It has got aluminum O6 octahedra. Adjoining to this is gamma L2O3, gamma alumina, which has got a cubic spinel structure. So for laser applications, you use alpha alumina. Alpha alumina is used as a laser host material. For example, ruby laser is nothing but chromium 3 plus doped in Al2O3. You don't make lasers by gamma alumina as the host. Likewise, gamma alumina is used as an active support of catalysts, because here we have got vacancies. We have got one oxygen vacancy and we have got cation vacancy also. So we have one vacancy of cation and one vacancy of anion. Because of presence of these point defects, gamma alumina has got high surface energy, and in turn it is a much better support, active support for many catalytic materials compared to alpha alumina. So for catalysis, you use gamma alumina, not alpha alumina, and for laser host application, you use alpha alumina, not gamma alumina. This is a typical example of role of structure in imparting a given functionality. How do we tailor the structure to get a desired property is nicely summarized in this slide. At the center, you see the structure of calcium titanate, perovskite structure, discovered in the year 1839, despite the fact that this was discovered almost close to 190 years back. This particular compound has got no applications. The reason is that too much of stability and too much of symmetry makes this compound devoid of any properties. So in turn, you have to move away from symmetry and you have to move away from high stability. So you have to go for low symmetry and low stability materials to make different types of functional materials. Replace calcium by barium, you introduce some distortion in octahedra at B side and you convert a useless material into an excellent ferroelectric material. You can create some oxygen vacancies by chemical jugglery, and at certain concentration, oxygen vacancies undergo ordering and you get a related structure which is called as brown millerite Pa2In2O5. This compound is used as oxide ion conductor. Replace calcium by lone pair ion like bismuth, titanium by magnetic ion like iron, and you get a wonderful multiferroic material BiFeO3. Likewise, you can make ferroelectric proton conductors. You can make multifunctional materials like CeCrO3. You can make ferromagnetic materials. You can make ferroelectric and ionic conductors. They are intergrowth materials, perovskite, fluoride, perovskite, fluoride. So between two perovskite slabs, you introduce a fluoride layer. So in this slide, I emphasize the role of structure in imparting a given property. This will be taught to you in details by my colleagues. Next approach is metastable approach. Metastable materials should not be confused with unstable materials. Diamond is metastable, but diamond remains diamond for millions of years because diamond does not become graphite by its own. It has got very high energy activation energy barrier, and that is called as kinetic energy stabilization of materials. So in our course, you will be taught a number of approaches of metastable materials. Metastability can be imparted by too high packing, by too low packing, low valency, high valency, ordered stage, disordered stage, unusually high coordination number, etc. All these things will be covered as the course further unfolds. Third approach which is going to be taught to you is defects engineering. You will be surprised to know, many of you might be knowing also, point defects are very crucial for existence of some materials. Some materials exist only because of the optimum extent of point defects. The classic example is yttria stabilized zirconia. Unless you introduce oxygen vacancies, cubic form of YSZ will not exist. At best, you can get tetragonal yttria stabilized zirconia, which is also called as partially stabilized zirconia. But for full stabilization of zirconia, you need to introduce some oxygen vacancies. And the thermodynamics behind this is as you introduce defects, you increase the disorder, you increase entropy, and in turn, you attain what is called as entropy-induced stabilization of meta-stabilization phases. A number of things I have arranged in this slide. I want to spend much time. All these things will be taught to you in coming days. Third approach is hybrid approach. Hybrids are not just a physical mixture of A and B. Hybrids are basically interacting two or more than two components in a given body. They have got role of interface, interfacial strain, defects at the interface, and at times these components have coupling effect also. They synergize the property of each other. So defects approach is one I showed in previous slide, and hybrid approach is the one I show in this slide. Hybrid materials are also going to be covered to some extent in this course. So what is the best course of action to make a material, or how to empower a functional material? So already I have discussed, I have emphasized repeatedly that first and foremost, you must master the knowledge of crystallography, wherein you know how to arrange atoms in a particular fashion, how to play with bond length, bond angle, how to optimize order, disorder, and defects and distortion. By all these things, basically, you get a functional material with the desired property. And to further empower it, you play with size and shape. You fine tune size, shape, morphology, microstructure, surface area, surface energy, and porosity. So this I call nanomaterials empowered by crystallographic concept, or vice versa also. Either way you can call. In nutshell, you make materials at the interface of crystallography and nano science. So that's how will be a major focus of the course in this package. We have a very dedicated portion in this course on synthesis protocols. Having said all that, I must emphasize, and rightly so, that unless you master the art of synthesis, materials chemistry is going to be a nightmare for you. So please learn all protocols of synthesis. And I may also add here, the synthesis is not learned by attending merely lectures. Lectures in this course are going to only give you a bird's eye view. But in nutshell, you have to learn synthesis by doing. Learning synthesis is like learning bicycle and learning swimming. Unless you go to water, you cannot learn synthesis. So our faculty members will give you an overview of different types of techniques like solid state method, soft chemical method, a number of other methods will be taught like high pressure synthesis, vacuum heat treatment, melt and quench technique for making glasses, and they also will expose you briefly about processing, how to make thin films of materials using inkjet printing, screen printing, spin coating, how to make a nano ink which will flow nicely. All these things will be taught to you. But let me once again repeat, the best course of action is that after course is over, please go to lab and use all this knowledge in making materials. Learning by doing is the best course of action as far as synthesis is concerned. After you make materials, next comes characterization of materials. Here, one can characterize the composition. When we say complete characterization of materials, it amounts to finding composition, finding crystallographic structure, finding microstructure, finding purity, impurity profile, finding local structure, what is the speciation, surface characterization. So in this course, a dedicated package is there on different types of analytical tools, crystallographic and microscopic tools. All these things will be taught to you so that you get exposed to different types of techniques. As I mentioned, you will be taught X-ray diffraction, neutron diffraction, techniques like XPS, AES, SEM, TEM, and some spectroscopic techniques also will be covered, and there will be lectures on X-ray fluorescence, neutron activation analysis, mass spectroscopy, etc. This list is not exhaustive. There are many more techniques which you will be learning during course of your PhD work. One thing I should share with you that our teachers, our faculty members are not like any other university faculty members who teach from nice books, etc. They are the people who themselves are highly experienced researchers. Even the youngest teacher also, among 5 of them, has spent more than 20 years in research. So they are the practicing scientists who will teach you all these things by their vast experience which they have gathered. So please do ask fundamental questions to them. And I shall encourage you to ask questions which are out of box, out of books. For example, when they teach you X-ray based techniques like X-ray fluorescence, X-ray diffraction, X-ray photoelectron spectroscopy, and OJ electron spectroscopy. So all these 4 techniques are what I call X-ray based techniques. You must ask them in what way X-rays interact with matter. So interaction of probe radiation with the matter is something which they will teach you, and you also ask them. Unless you know the interaction of X-ray with matter or interaction of electrons with matter, when the concerned faculty member will teach you electron microscopy based techniques, that time he or she will tell you the basic mechanism, the physics behind interaction of electrons with matter, or for that matter, interaction of neutrons with matter. These are the things which will be quite out of box, out of book in this syllabus, which I am sure will be useful in your career in coming years and decades. Some more examples of how structure can play a very big role. Structure can drive phase separation. A simple example, perovskite is shown here, fluoride is shown here. Perovskite structure AbO3 cannot tolerate any anion excess. You cannot make AbO3 plus X, whereas fluoride structure can tolerate anion excess as well as anion deficiency because there is a crystallographic void 111 which is vacant. Unlike perovskite, in perovskite you don't have any Wyckoff position where you can stuff X with oxygen. So perovskite structures and also structures of other cubic close packed lattices have been used to get some chemistry at industrial scale. Next slide you will see aluminum industry and titanium industry are using these crystallographic concepts since decades at very large scale. You know aluminite is an ore, FeTiO3. It is cubic close packed lattice, corundum structure, you can see here. How to separate iron and titanium oxides from this lattice? Simply gently heat it. And O3 plus X, it is not going to tolerate at all because there is no vacant position. By slight addition of oxygen, there is a phase separation of ilmenite into corundum and rutile. So this is the kind of power of crystallography which you will learn from this course. Likewise, UO2 becomes U3OA and then you dissolve. All these things will be taught to you, the role of structure. Likewise, there are experienced faculty members who will expose you how to tailor a structure, how to make a one-dimensional tunnel structure into layered structure. These are the concepts, believe me, you will not find in any book. All these concepts will be taught to you by people who have made these compounds. So this is the structure of K2CePO4. It has got one-dimensional tunnel and it's a framework structure. It has got a frame of PO4 tetrahedra and CEO8 polyhedra. So you replace cerium by zirconium. In this process, ionic potential increases considerably. And in order to stabilize the structure, to minimize the repulsion, this one-dimensional tunnel structure undergoes slicing. And by slicing, you get a layered material. So how a tailor master does slicing of a cloth to make a suit for you. In crystallography, you can do slicing, you can do stitching of building blocks. You can stitch building block to get desired structure. These concepts will be taught to you by my colleagues, which are not available in any textbook. I can go on talking. There will be some slight coverage of high pressure synthesis. I think one of the colleagues is going to teach this part. Then there will be a separate module for analytical methods at different mass scales, right from volumetric and gravimetric scale, which is at 100% level, you go to 1% level, microgram level, 100 microgram, 1 microgram, nanogram, picogram, femtogram, and there will be exposure to you on what are the techniques available at single atom. So an entire plethora of techniques as a function of mass scale will be covered in this course. I should now try to conclude my talk. Those of you who are from DAE or for that matter outside DAE, materials are going to play a big role in all major science and technology department. This slide is not for DAE alone. Same is true for ISRO. We had Chairman ISRO just 2 days back with us, and he also showed more or less same type of concept. So those of you who are going to take this course will get benefited. In particular, those of you who are working in DAE or ISRO kind of organization or DA or DRDO, because these organizations use a large number of materials such as oxide, fluoride, nitride, silicide, metal, intermetallics, alloys, carbon-based materials, polymer, organic compounds. All of them will be covered in the course. Different properties of materials, high density, porosity, nano, soft, inert, reactive, luminescent, transparent, radiation opaque and shield materials. Functionalities, absorbent, ion exchanger, sensor, detector, catalyst, oxidant, reductant, defective solids, semiconductors, scintillators, composites, multilayers, applications under high temperature, high pressure, extreme radiation field, highly corrosive environment, high ionic strength environment, highly abrasive environment, and high electric and magnetic field. All these applications need you to learn materials chemistry from different perspective, and that is our aim. Incidentally, please also remember this 30 lectures course, 6 credits, definitely is not going to make you an expert in this field. It is going to introduce you. Your expertise will begin after the course is over. This course is basically to expose you to a wide range of materials, properties, functionalities, applications. And to become expert, I can say you have to slog year after year and decade after decade before you call yourself an expert. That's how most of us have done in our career. What are the materials for future? One has to make hybrids of living, non-living. One has to make materials which are environmentally benign. So after their life is over, they should degrade themselves. They should be amenable for recyclability and develop green protocols for synthesis. Metamaterials, they are quantum materials, metastable materials, materials consisting earth-abundant elements. Can you replace ruthenium-based electrocatalyst by zirconium, silicon, aluminum-based materials? A big challenge is waiting for your generation. Biomaterials, which will have self-healing properties. They are polymers which heal, and our body is full of materials which has self-healing property. Materials for environmental remediation is another research area waiting for you to be explored. So I asked you a question in first slide, what is materials chemistry? After end of about half an hour lecture, answer is materials chemistry is nothing but concept of chemical bonding, concepts of crystallographic structure, fine tailoring of radius ratio, RC by RA, cation to anion ratio, fine tailoring of counter-ion polarizability, polyhedral packing, coordination number, bond distances, angles, and optimization of disorder, distortion, defects, in particular point defects. Innovative yet simple synthesis protocols, materials chemistry beyond thermodynamics and phase diagrams. These are the things you will be exposed to in next 30 lectures. This course, I have told you repeatedly, will comprise of general materials chemistry, characterization techniques, chemical, major, trace, and ultra trace analysis. Recall my slide on techniques at different mass scales, and you will have a good coverage of functional materials, magnetic, energy, etc. Some books, these books are published by me only. Advanced Techniques for Materials Characterization will be useful to you. Functional Materials, published in 2012. Materials under extreme conditions, and during lockdown and semi-lockdown period, we published a book series, a handbook on synthesis strategies for advanced materials. All these 6 books, I'm not saying they are authored by me. I'm not saying because of that at all. They are doing very well commercially. So I'm not here to make advertisement of these books. But I must say that all the 6 books will be useful to all you young colleagues who are embarking upon a great journey in the field of material science. Here are our 6 faculty members. Dr. R.K. Singhal, a very experienced scientist. He'll be teaching you analytical techniques in this course. Dr. A.K. Chauhan, he could not join today. Dr. Dimple Datta is sitting here with us. She is an expert in the field of functional materials. Dr. Vinita Gupta already she introduced herself to you. She will teach you first module of the package of the course, wherein she will discuss different concepts. Dr. K.C. Barik, a young faculty member, all 5 of them are very well-established scientists and have excellent recognitions from different bodies of science and technology, India and abroad. All of them have done, they have got good exposure in Indian labs as well as international labs. And as I mentioned in the beginning, that they are going to teach you all these things much beyond a regular textbook can offer you. With this, I must thank Professor P.R. Vasudevarawa, VC HBNI, Professor P.D. Nayak, Dean HBNI, Dr. Anshu Singhal, who is helping me to coordinate this course. Faculty members, already I have mentioned their name, and it goes without saying, I need to thank all the participants who have joined this course, and I hope this course will be useful to you. At the end, I look forward to get good feedback from you so that next edition of the course, 1 year down the line, when we start, it is better than this edition of the course. Thank you very much.
Uh, so Dr. Tyagi has very nicely summed up what is it that you should be expecting from this course. So he has already introduced all the lecturers. First module I would be taking, wherein it would be kind of hand-holding you to advanced material chemistry. So I would be starting from the very, very basic concepts that probably you would have started studying from your 12th onwards. That includes unit cell, lattice planes, and Bravais lattices. And you will move on to simple structures and then further move to complex structures. We'll talk about the synthesis protocols. We'll talk about defect, disorder, phase transitions. And at the end, I would also like to address the holy grail of materials chemistry. That is how the structure affect the properties and how material scientists tune it to their benefit. We'll take few examples that would make it more clear to you during the course of next 7 lectures. So we'll just take 2 more minutes before we embark on formal lectures. Now, I would request Dr. Kanu Barik, who would follow my module by his characterization module, just to introduce him to yourself, you people, and just give a brief description about what he would be covering in this particular part of the course.
Thank you, madam. So I'm Dr. K.C. Varik, as Sar has already introduced me. So mainly I will cover second module of the course. So that mainly covers the characterization techniques, where I will teach about the interaction of matter with the X-rays, neutrons, and electrons, and also different instrumentation techniques based on this interaction of matters. Like, for example, I'll talk about X-ray diffraction, X-ray fluorescence spectroscopy, X-ray photoelectron spectroscopy, as well as small angle scattering, and in addition, the neutron scattering and neutron diffractions. And in addition to that, I'll also cover, with some repetitive examples and, data analysis of all these techniques. In addition, that some of the imaging techniques like electron microscope, optical microscope, and also this electron microscope. I'll briefly discuss, scanning electron microscope and transmitting electron microscopes with some repetitive, examples giving emphasis on especially the interpretation of those like the microscopic structures. So that I'll cover briefly. In addition, that some other techniques, surface techniques that like secondary ion mass spectroscopy, XPS, and other electron spectroscopies. So those characterization techniques will be covered with brief examples, and that will give an brief that overview of different characterization techniques. So in this second module of the course. Thank you. And Dr. Dimple, that he will mostly cover the next module of the lecture. And
so the third module will be actually covered by Dr. Rakesh Singhal, who will be teaching you about all the different trace analysis methods. And I will be actually covering the fourth module, which is functional materials. So after all your basics and synthesis and characterization, all these background has been developed in your mind, then what we will go into is what are the different kinds of functional materials we have. The functional properties which we'll be looking into are mostly magnetic and also energy storage, energy conversion. So we'll be talking a lot about batteries, we'll talk a lot about supercapacitors. We'll also cover magnetic materials, where we'll talk about ferromagnetic materials, we'll talk about RAM, we'll talk about how memory devices are getting changed over the time. And also we will be having a short module on photocatalytic as well as electrocatalytic materials. And Dr. Chauhan, who will be following the fifth module, that's the last module of this particular course, he will be covering thermoelectric materials. He will also be covering a lot on photovoltaic devices and semiconductor materials. So with this, I think you will have a proper overview, starting from basic concepts of materials chemistry to its synthesis, to characterization, to different properties, and also how you are going to tune in the materials to enhance the properties whatever you will be seeing. So with that, I think the overview of this particular course comes to an end. And now I would request Dr. Vinita to start with her lectures for today.
So here we are starting our course, the lecture 1 of Advanced Material Chemistry. I hope to spend very nice next 7 lectures with you. I would request you that today's lecture I would cover only basics. This is now another 35 minutes of time that we have left with us today. Would request you to type in whatever questions you have in the chat box. Please note down my mail ID, and you're very welcome to ask any question, any doubt that you come across in whatever I teach, or you find it somewhere else. Whatever I teach, you go and refer to some other books. You find any doubt, any clarification, you're most welcome to come back and clarify it with me. So with this, my module is labeled as General Materials Chemistry and the Basics. Most of us have actually started, nowadays kids started pretty early in class 9th only about solid state chemistry, but most of us started it somewhere in 11th, 12th. And then the materials chemistry was known as solid state chemistry because it would deal with solids. Dr. Tyagi very nicely summed up why should we study material science? Okay, the word our society needs constant advancements. Advancement depends on new techniques, new technologies. New techniques and new technologies depend upon new materials, whether it is, yes, energy. Energy is the question in today's world, going to more renewable sources of energy. Everything that you can think of for the development, for the advancement of humankind, basically depends upon how developed the materials are. And what does development of materials mean? Getting better properties out of them. How will you get better properties out of them? Properties depend upon what that material is composed of. That is its composition. And in the same composition also, what is its structure? And nowadays, of course, even the microstructure that can be tailored. So basically, if you want to get good properties, you need to know about the structure. Okay. So for that, it is very essential to understand the relation between the two. Suppose I know which key opens the lock. What is the design of the key that will open this lock? Now, given that understanding, if I have to develop, advance, make, fabricate new keys, I will have a rough idea. Okay, this is the key that opens this kind of lock. So if I want to open a similar lock, these are the characteristics of the keys that I should be developing, right? So this is what, in more technical terms, we call as structure-property relationship. And that is why it is important to understand materials and material science. Okay. Going from the very basic concept, what is a material? It is a substance or the mixture of substances. And hence, material science is the study of properties of the material and how these properties are governed by the composition and structure. So basically, on an average, when we talk about materials, we talk about two materials, either two kinds. Either they could be crystalline, and when we say crystalline, all of us know that they have long range, three-dimensional periodic arrangement of the structural unit, which we can call as unit cell or we can also call as lattice point. So they have a regular repeating pattern. But amorphous material, they lack long range periodic arrangement. We know all of us glasses. So there is certain difference between glasses and amorphous material also, which probably we will discuss sometime later in the duration of next 7 lectures. But yeah, the point is that they lack long range periodic arrangement and there is no repeating unit that you can establish by overlooking their structure. So, and then now we have a new class, of course, not the new class, but we say nanomaterial. And if you kind of think about it, basically, when you go from crystalline solids to the, how do I do this? When we go from the crystalline solid to the amorphous solid, okay? What we are doing is we are basically decreasing the order of that long range periodicity, the distance, let's say over the distance, that periodicity regime is being shortened. And somewhere in between, we get nanomaterials, okay, where the materials crystallinity is still observed. The grains are still enough that you can observe some kind of 3D periodicity, but it is not on as long a scale as available in normal bulk crystalline solid. All right. Now, so going to the very fundamental concept is what I call as unit cell. Unit cell is the smallest repeating unit that describes the full symmetry of the crystal structure. So if I ask you, how would you choose a unit cell? You would say it should have minimum volume, but that minimum volume should be able to explain all the symmetry or the symmetry elements of your crystal that you want to identify or that you want to work with. Okay. Now, suppose you look at this array of points. I can say the minimum unit could be these two red and blue atom also. But because ultimately three-dimensionally you are repeating the red and blue atoms also as well, right? But your whatever minimum chota volume that you choose should also be able to express the maximum symmetry. And hence, the next two representation show how you can choose the unit cell for this 2D arrangement. When we go to 3D arrangement, then there are other factors that come into play as well. Okay. So, like for example, we have yet not gone into NaCl structure, but most of you might be knowing about it. This particular figure is taken from AR West. If you want to know the books that we refer to, I'm sure Dr. Anshu Singhal has forwarded you the list of books as well. But whenever in doubt, I first of all, before going to other literature and other resources, I refer to AR West. That is my favorite book. You can refer to it as well. Okay. So first is it when you see the NaCl crystal from the top view, this is how the A structure shows you. This is how it will look like. Let's say the unfilled circle is the Na atom and the filled circle is the Cl atom. And how can I decide the unit cell? I can decide it by joining the units as I've done in B. Perfect. Like C, perfect. I've simply changed the origin from Na atom to Cl atom. I can also do D. There is no problem in that because your corners and the lines need not necessarily fall on the atoms. So that is also right. But will come E is can be chosen as a unit cell if I'm talking in 2 dimensions. But if I go in 3 dimensions, if you try to visualize it, probably it will not cover all the symmetry elements of NaCl structure, and hence this is not the correct structure in 3D. F, definitely a no-no, because your unit cell, whatever unit cell you are defining, the corners, the lines need not necessarily fall on lattice point, but they should cover the entire volume. Here we have some space, as you can see in between, which are not covered, and hence this is not the correct representation of unit cell for the array of points that are defined by A. Okay. Unit cell parameter, because we would be talking about it. So I thought it's a good idea to tell you when we say unit cell parameter, what do we mean is what are the dimensions along X, Y, and Z axis, which we normally refer to as A, B, and C, and the angle alpha, beta, and gamma. So alpha angle is basically opposite to alpha is opposite to A, beta is opposite to B, and gamma is opposite to C. We can refer to whatever angle we want by whatever name we want, but this is a convention followed in the literature. So if right from beginning, we develop the habit of getting to know this convention, it becomes easier to refer to the literature and understand what the other authors want to say. Okay, now since we are slowly developing on concept, we've also read about 7 crystal system and essential symmetry elements. So what are 7 crystal system? Basically, there are 7 independent unit cell shapes that are possible in 3 dimensions. Okay. Now, till now, all of us, including me, till a very long time, we used to say 7 crystal system, 7 different shapes. And then once we know that this is the shape, we would say it would have these particular symmetry elements. Now, as Dr. Tyagi mentioned that we would try to particularly, give you a different flavor of the concepts that you have learned till now. Basically, it is not that you have a particular shape, hence it would have those particular symmetry elements. Rather, it is the ulta, it is reverse. Because that particular structure to represent its 3-dimension periodicity should have those particular symmetry elements. And we consider a combination of symmetry element, we as a result get that particular shape. Just to give you the example, let me just first read it. So basically, 7 crystal systems are governed by presence and absence of symmetry element. Shapes, I repeat, do not define the unit cell. It is rather the presence of symmetry element that decide the shape of the unit cell. For example, normally what we would say that when we have a cubic unit cell, it should have, read first, it should have A is equal to B is equal to C, alpha is equal to beta is equal to gamma is 90, and hence it should have 4 3-fold axis. No, it is because your cubic unit cell should have 4 3-fold axis. When you apply these 4 3-fold axis, the 3-dimensional figure that you would obtain would be a cubic unit cell. That means the 3-dimensional figure that you would obtain will have A is equal to B is equal to C, and alpha is equal to beta is equal to gamma is 90 degrees. Okay, so I hope it is clear now. So when we say a cubic unit cell, we say that getting the 3D periodicity of that particular structure, 3C3 is the essential criterion. And of course, once you have 3C3, other symmetry elements like 3C4, they will follow. And whatever you result with is a cubic unit cell. Okay, just to show you, get you into the flavor, where do I expect my C3 axis in the cube? It is across the body diagonal shown here. Okay, so just imagine your dice with which you play your Ludo or whatever, and then hold it like this across the body diagonal. Now, when you rotate it, okay. Now, when you rotate it along this particular axis, this corner this corner will go to this corner when you move it by 120 degree. Okay, so you will get 3 such similar this thing till you reach the original thing. Hence, we say it possesses 3C3 axis. Okay, anyway, here I'm only trying to show where the axis pass through. So if you have a hexagonal unit cell, this is how, when I say that it contains a C6 axis, this is how it looks like. So when we say that a particular structure has got a C4 axis, this is how it looks like. If this along this axis, you try to rotate it by 90 degree, you get a similar configuration. So those who have studied group theory will know that when we say similar, it is different to when we say identical. Okay. And okay, C3 we have already talked about, and C2 again. This C3 was against the body diagonal. So in drawing, it might be looking similar, but C2 is basically, if you hold your cube in such a way, this is basically your edge, and this is again an edge. So the C2 passes from one edge to other opposite edge, and you will, if you rotate by 180 degree, you will get the similar configuration. Okay. Now this particular slide kind of sums up the 7 unit cell shapes or the 7 crystal system that exist in materials in the world of solids. Cubic, you know, that's the simplest system to remember. All the axes equal, all the angle equal, you have, and they are equal to 90 degree. Tetragonal, you elongate your cubic along any one of the axes. Generally, we say along the C axis, wherein your C axis is either shorter, or bada, longer than other 2 axes, which are equal. All your angles are still 90. Orthorhombic is like your shoebox. Okay, A is not equal to B, is not equal to C, but all the angles are equal and 90 degree. Hexagonal and trigonal, basically they belong to same kind of this thing. There is a slight difference which if we get time, we'll come back to it. So here your A is equal to B, again is not equal to C. C is either longer or shorter. 2 angles are 90, one is 120 degree. Okay, like this thing. A is equal to B is 90, but gamma is alpha beta are 90 and gamma is 120. Okay, monoclinic is you take your shoebox, put a hand on top surface and apply a pressure. It will distort. What will happen? Anyway, A was not equal to B, was not equal to C. Your alpha and gamma are still 90, but now your beta distorts when you slide it this way, and it is now no more 90. Triclinic has nothing equal, none of the cell parameters are equal, none of the angles are equal, and they're not even equal to 90 degrees. So that is triclinic system. Okay. This slide just shows whatever we discussed in previous slide. Okay, lattice. Now what is lattice? Lattice we know is three-dimensional array of points which we can use to represent our crystal structure, atoms or ions in the crystal structure. Okay. Now looking at the figure, each lattice point here describes either sodium or chloride. But as I mentioned on the second slide, it is not necessary that you should have your atom at the lattice point. For example, I have Na, I have Cl. So I can draw my lattice point here. But it is also perfectly okay if I draw my lattice point here. Okay? Because repeating these center point also will create the same lattice as I would have created if I had put the lattice points exactly on Na and Cl. Okay. So a lattice point may or may not contain an atom or ion as long as it represents the 3D periodicity similar to what my atoms and ions in the crystal structure are representing. Okay. Again, an interesting point. If we join our lattice point in the way I have joined in the A pattern, okay, then here my lattice has got more than one atom because the 4 at the corners represent 1 by 4 each and 1 in the center represent 1. So it has 2 atoms. It is called a centered lattice. But when I represent it in the way as I've represented, when I joined them in the way as I've joined in B, this is called the primitive lattice. Basically, for every structure, it is possible to draw a primitive unit cell that contains only one lattice point. Now, what is the advantage of that? The crystallographers use it to make the representation rather similar. Okay, simpler, not similar. Now, what is a basis? Most of the time when we ask students this question, some of them know it, most of them don't know it. So basis is basically, it is like this. Okay. In previous slide, I told you that you can, make your lattice point in the center also. Now, so I have a 3D array of points. Okay. What I should place on that particular point so that I can generate my structure. So that 3D array of points is called lattice. Whatever I am planning to place on that 3D array of points is called basis. Lattice plus basis is called the generate your crystal structure. For example, you see this. This is your space lattice, array of point. I have to generate this particular structure which I have shown here. So this is my lattice array of 3D point and this is my basis. This basis, if I place on my lattice point, I will be able to get the structure that I want to generate. Similarly, this is my space lattice and this is my basis. To generate this structure, I put this particular basis on these lattice points to generate this particular crystal structure. Okay. So, a crystal is defined as a lattice with bases added to each lattice side, and your basis can contain of one atom, it can contain of group of atoms, it can contain a molecule. I hope this is clear. Okay. Now, different lattice type. We talked about crystal system. Crystal system is the shape of the unit cell. Okay. Now, how that unit cell has got atoms arranged on it, that is decided by lattice type. That is how we classify the lattices. So, there are 4 main type of lattices that we have. One is your simple cubic, wherein all your lattice points are at the corner of the cube. Then we have base-centered cubic cell, wherein one particular pair of your faces, either it is along the C axis or it is along the A axis or it is along the B axis. Only one pair of atom is centered. That is called base centered. If it is along C axis, we call it C centered. Along B axis, we call it B centered, and by similarly for A centered. Body center. you have the lattice point on the corner of the cube as well as in the center of the body. That is denoted by I. Okay. Primitive was denoted by P. Side center, depending on whether it is A, B, or C, is denoted by that particular letter. Body centered by I. And when all your faces are centered, we call it face centered. Okay. Going through basics once again, very basic thing, because we would be needing these things when we will study structure. Whenever we have corner atom of the cube, it contributes because each corner is shared by 8 cubes. 4 in the bottom layer, 4 in the top layer. So each atom is shared by 8 cube. Hence it contributes 1 by 8 to a particular cube. When you have a body centered atom, it is completely lying into that particular cube. So it gives entirety of itself to that particular cube. It contributes 1. When you are face centered, because each face is shared by 2 adjacent cubes, so each face lattice point contributes half. So if we have all the faces centered, so we have 6 faces on a cube and each face center is contributing half. So 6 into half, all the face centered will contribute 3. Okay. So I hope it is clear that, so that means your primitive lattice has got 1 lattice point per unit. Body centered has got 1 from the corner, 1 from the body center. So total 2 lattice point per unit. Face centered has got 1 from the corner, 3 from the faces, 4 lattice points per unit cell. And side center, 1 from the corners, half from the opposite faces, 2 lattice point per unit cell. Okay. Now what are Bravais lattices? Okay. So Bravais lattices is nothing but the combination. We studied about the crystal system. We studied about the lattice type. So Bravais lattice is a combination of the unit cell type and the lattice type. Okay. Now there are 7 crystal systems and there are 4 lattice types. That means how many Bravais lattices should we have had? 28. But the feasible combinations of Bravais lattices is only 14. 1, 4. If you go and read wherever, they will tell you that there are 14 Bravais lattices possible. Why don't we have 28? 7 crystal system, 4 type of lattice type. I should have had 28. The reason is because certain combinations are not allowed or they are repeated or they can be represented by a smaller unit cell. And remember, our definition of unit cell says that whatever unit cell you are choosing for a material should have the smallest volume possible if it is able to represent all the symmetry that is required for that particular crystal cell. For example, you look at this, okay? Let's say example 2, that is the easier one. What is it? It shows you 2 cubes which has end centering, okay? So you have end centered cubic cell, okay? Now, let's say the lattice parameter was A. All right, now, but it is possible for me if I join this and what I will get this, okay? Now, everything, all the lattice points have been covered. I've not left anything, right? Here, this was end-centered cubic. Now, what I have resulted is, it is a simple tetragonal. And why will I choose this particular cell over this one? There is a reason for that. What was the lattice parameter for the left-hand figure? A. Now, if this was A, all of you would agree with me that this particular line is root 2A, right? Because this is A, and this is right angle. So this particular line is root 2A. Now, if this is root 2A, this is root 2A by 2 or A by root 2. That means now earlier unit cell had the cell parameter of A. This particular unit cell has a cell parameter of A by root 2. That means I have got a unit which can still cover all the lattice point, which can still represent the entire symmetry. but its lattice parameter is smaller, its volume is smaller. So this is the unit cell that I would go with. That means even though there was one particular combination was there in that 28, which had end-centered lattice combined with cubic unit cell, but I will not choose this because it can be represented by something that I call as simple primitive tetragon. And this is how some of the combination they cancel out. And that is why even though we have 7 crystal system and 4 lattice types, we do not have 28 Bravais lattices. We have only 14 Bravais lattices. Okay. So this particular slide, since the talk would be loaded on YouTube and probably it would be sent to you also, you can look at it later on. This particular slide lists all the 14 types of Bravais lattices that are possible, that are feasible, without any repetition, smallest unit cell, maximum symmetry, that are possible when we study the crystal symmetry of the materials. Okay. Now, what is an important condition? There's another important condition for Bravais lattice. What it says is, the arrangement of the lattice point around each and every lattice point of the Bravais lattice should be similar. For example, you look at this particular structure on your left hand side. Now you have a look at any point you want. This one or this one or this one, all of them have got similar environment. Okay, so this particular lattice, even though it is in 2-dimensional, it can count as something which is similar to Bravais lattice. Now this is a honeycomb structure of the graphite. Okay, but this is not a Bravais lattice. Why it is not a Bravais lattice? Let me take your attention to 3 particular points: P, Q and R. Okay, now you look at P and Q. The surrounding of PR, that it has this line, and this line. Okay, this is similar to what we have in Q. It has the nearest neighboring arrangement are this way, and this way. Okay, now but you look at R. Its nearest neighboring arrangement is this way, and this way. So basically the arrangement around R is 180-degree opposite of what is the arrangement around P and Q. So all the lattice points do not have similar 3D environment, and hence the honeycomb structure or this particular structure that represents graphene is not considered as a Bravais lattice. I hope that is clear to all of you. If not, you please post the query. Okay, now since we have to start the concept of lattice plane Miller indices, we will take it in next class only so that we have a continuity when we do that. We would probably now, we will wind up this class here since this was an introductory lecture to give you a flavor of what we would be studying. I covered all this. If you have any query, I would report. Please post it to me. Please post it in the chat box. Don't carry any doubt with you. So we would close here, and I would look forward to meeting you on Wednesday at same time. I hope everything is clear. We have 2-3 minutes if you would want to ask anything about the course, about today's lectures, anything at all. It would be wonderful if we can interact. Like today we had only 30 minutes together, but maybe next lecture onward, probably every 15-20 minutes, it would be wonderful to listen from you, whether you're understanding everything is all right. Gopinath, yes, gels are amorphous unless we are able to quench the gel and grow crystal out of them. Normally, we would say that gels are amorphous. Yes. Okay, so probably we can close here today, but I would really appreciate About the honeycomb structure. Okay, I'll just go back to, give me a minute, please. See, this was regarding the Bravais lattice, okay? So when we say that this particular lattice is the Bravais lattice for this particular structure, then what we have to ensure it that every point that we have chosen as a Bravais lattice should have similar environment around it. When I say environment, I say arrangement of lattice point around the point of our interest should be similar. For example, in this particular structure, suppose I choose, this is a very, very simplified example. I choose this point, okay? It has now 1, 2, 3, 4 nearest neighbor. Let's say if I say the distance between two of them is A, so it has 4 at the distance of A and 1, 2, 3, 4, 4 at the distance of root 2A by 2. Okay. Now similarly for this atom, now similarly for this atom, and so on. But if I come to this particular structure, what happens is you choose any 3 points. I've chosen any 3 points. I've chosen P, I've chosen Q, I've chosen R. Now what is the arrangement of other lattice point around P, Q and R? If this indeed is a Bravais lattice, the arrangement should be similar. So around P, what I have is, it is joined to next nearest neighbor this way, and this way. Okay. For Q, it is joined this way, and this way. Right. Now let us come to R. How is it joined? It is joined this way, and this way. So basically, only if you just concentrate on these arrows for P and Q and this particular arrow for R. If you see the array of points, if I'm standing at P and then if I'm standing at R, basically the entire scene for me is rotated by 180 degrees. Okay, that means the arrangement of array points or the arrangement of lattice point around all the atoms are not similar. And that is an essential criteria for Bravais lattice, that the arrangement of the array points around any point, you go and stand at different point, what you should be able to view should be similar from any of the point you go. So that is not particularly happening in the honeycomb structure. So this is not a Bravais lattice. I hope it is clear now. So maybe we can wind up here and we shall discuss more in the next class. Thank you.